All right, so here's a few things. By the way, hope you had a nice fall break. This is week number 8. So after this week, the semester is halfway over. Okay, a few things. Homework 5 is due tonight. There's probably going to be 10 homework assignments, so that's halfway also. So the plan is today we will talk about chapter 10 some more, and then save like the last 20 minutes or so. If you have any homework 5 questions, we can talk about those then. Homework 6 is coming up. It's over chapter 10, and it's due a week from today. Okay, that's a little bit long, 14 questions, so don't wait till the last minute to do that. Lab Thursday is completely online. Don't show up Thursday. It's a skate park lab, so it'll be available tomorrow, and I'll send out an announcement when it's posted. Okay, any questions on the upcoming administrative type stuff? Okay, so this is what we were working on previously. This is work, so I use a big W, force times the distance that you go through, and then we'll see what this cosine of theta means in just a minute. What does it give you? So if you have a force through a distance, it actually gives you something, and it's the change in kinetic energy. So when you look through the book, they just call it K for kinetic energy. I call it KE for kinetic energy. The reason you'll see later on today, I think. So the final kinetic energy minus the initial kinetic energy. And kinetic energy is 1/2 mv squared. So 1/2 mv final squared minus 1/2 mv initial squared. Now the use of this is, if you have the force, the displacement, the mass, maybe you want to calculate the velocity, that sort of thing. So whenever the problem involves these 4 quantities, you'll have to be given 3 of them, and then you'll have to figure out what the other one is. You could use Newton's second law along with kinematics to solve a lot of these problems. This just makes it a little bit easier for you. Okay, so any questions on that? All right, so let's get into chapter 10 a little bit more. Excellent. So work is force times distance, but really it's the parallel part of the force that's lined up with the displacement. We'll see what the picture of that looks like in just a minute. As far as units go, this is force, which is in newtons, displacement, which is in meters. So a newton meter turns out to be a joule. Okay, when it says work energy theorem here, that's what I just showed you on the document cam. So let's look at one example, and then you'll see what this angle is on the next slide. So Sarah pushes a heavy crate 3 meters along the floor at a constant speed. Okay, so we've seen this before, constant speed. It's not speeding up. She has a force this way. There must be friction back the other way, or it would be speeding up. So 3 meters, her force is 70 newtons. How much work does Sarah do on the crate? So work is force times displacement. They're actually lined up with each other, right? It's Sarah's force is to the right. The thing is moving to the right. They're lined up with each other. And we want to figure out the amount of work. Okay, so this one's not too bad. So we've got normal force. Here's the weight. That's not the work, that's the weight, remember? I'll just call this like force push. That's from Sarah. There's got to be friction back the other way. And we know that they must be equal to each other because the crate's not speeding up. So the work done by the push, it's the force, and then the distance that we're going through. And they tell us these in the problem. This force is 70 newtons. And the distance that we're going through, 3 meters. So the work by the push force here, 70 newtons times 3 meters, so 210 joules. Okay? So why isn't it speeding up? Well, the answer is there must be some work done by friction. The work by friction is negative 210 joules. So if this is 70 newtons, this force, this one's got to be 70 newtons back the other way. So if it's moving this way, and the force is back that way, that's when the force is, that's when the work is negative. They don't ask about this part, I just threw that part in. Now the normal force does no work. It's moving this way. The normal force is this way. There's 90 degrees between those. The normal force isn't doing any work. In other words, it's not making it speed up, not making it slow down. In this example, the weight is not doing any work either. The crate's moving to the right, weight is straight down. No part of the weight force is lined up either with the displacement or against it. Okay. All right, very good. Any questions on this one? All right, very good. All right. So this is more of a general picture. The force doesn't have to be completely lined up with it. Here the force is at some kind of angle, but the part that's actually making this cart speed up is the parallel part of the force, this part of it. So if you had the displacement this way, here's the force, here's the angle between the force and the displacement. This leg over here is F cosine theta. So in the formula up there, that's just giving you the parallel part of the force. By parallel, I mean the part that's actually lined up with the way that you're going. Now if the angle between F and D is 90 degrees, like it was with the weight and the normal force, the cosine of 90 is 0 and there is no work. Now if you're going to the right and friction would be back to the left, the cosine of 180 is -1. Okay, so friction always does negative work. Okay, so that's where the theta comes into play. We can take a look at some different scenarios. Here's initial velocity, here's a later velocity. These are actually lined up with each other. So the work is FD. If you wanted to, you could say cosine of 0, but the cosine of 0 is just 1. Here's where you have some sort of angle between the displacement and the force. So the cosine of the angle here just gives you the part of the force lined up with the way that you're going. So still doing positive work. Here the work's actually 0. The crate is moving to the right. The normal force is up. It's not doing any work. This force turns out to be, the work by this force turns out to be negative. It's moving this way. It must be slowing down though, it looks like. So the work is negative. It's making it slow down. Okay, good. Okay, this is the one where it's completely the opposite way. So it's moving to the right. Maybe you've lassoed it somehow, this crate, and now you're trying to slow it down. So here's the initial speed. Later on, not as big. It's been slowing down. So here the work is also negative. You could do cosine of 180. That's perfectly good. Cosine of 180 is -1. Or you could just realize if you're moving one way and the force is completely the other way, the work is going to be negative. The negative sign just means it's trying to make it slow down. Okay? Here's another example. A strap incline at 45 degrees pulls a suitcase through the airport. Maybe you've actually done this sometime. The tension is 20 newtons. How much work does the tension do if the suitcase is pulled at 100 meters at a constant speed? Okay, so let's take a look at this one. Okay, so here's the picture. I'll just represent the suitcase as a dot here. Normal force, tension, here's the weight. Constant speed must mean that there's some kind of friction back this way. Okay, we know a few other things. Here's theta. Now this is the part of the tension in the x direction. Here's part in the y direction. The part that's actually propelling the suitcase forward is Tx. The overall tension, though, we know is 20 newtons, and we're going through 100 meters. Okay, so if this were on a test, again, I would give myself probably 4 out of 10 already. And I want to figure out the work done by the tension. That would be this part here. So really, the work by tension in the x. So it's the force times the distance. But it's the part of the force that is parallel to the way that we're actually moving. Okay? So from the picture here, if this is theta, this is t, ty, and tx, the cosine of theta is the adjacent side over the hypotenuse. So t cosine theta is tx. And then I can plug that in here. Now if you want to, you could actually get a number for this right away and then put it in over here. So I'll just do it like this. T cosine theta times d. Okay, so 20 newtons cosine of 45, and then times 100 meters. So I think this is like 1414 or something like that. Let's check it out to make sure. So we got 20 cosine of 45 times 100. Good, 1414. The cosine of 45 is one that you could remember without too much trouble. And then times 20 and then times 100. Okay? All right, excellent. Square root of 2 over 2 is what it is. All right, good. So that's the work done by the tension, and it's completely in the x direction. It's not speeding up, so friction must be doing the same amount of work just in the, because friction's in the opposite direction. Great. Any questions about that one? All right. So sometimes forces don't do any work. There's a couple of situations. We saw a couple actually. If the force is perpendicular to the displacement, like the crate sliding across the ground, normal force was up, weight was down, it didn't do any work. But there also is no work if there is no displacement. So in everyday life, if I'm just holding a book in my hand, it gets really heavy after a while, but I'm not really doing any work in terms of physics because I'm not putting that force through any kind of displacement. Okay, so not all forces do work. I thought we could look at a couple from homework 6. Okay. So this is the first problem on homework 6. 1.4 kilogram book is lying on a 0.74 meter high table. You pick it up and place it on a bookshelf 2.3 meters above the floor. Okay, so it's at 0.74, and you're going to put it at 2.3. During this process, how much work does gravity do on the book? Okay, and then part B, probably how much work do you do on the book? Let's see. How much work does your hand do on the book? Okay, and the units here are joules. Okay, so as you take the book from the table, put it on the bookcase, the book is moving up, the force of gravity is down, so here gravity actually does work, and it's negative. It's because the book is moving up, but the force of gravity is down, so the work by gravity is negative. Now if I were to take the book and drop it, it moves down, the force of gravity is down. That's where gravity actually does positive work. It would actually make it speed up, right? If I took a book, dropped it, force of gravity is this way, it moves that way, gravity's doing positive work. On the other hand, if I took a baseball and threw it up into the air, it's going up, force of gravity is down, gravity is doing negative work, making it slow down. Okay, so gravity could either do positive, negative, or no work, as we've seen now. All right, let's take a look at this one. Okay, so initially this is on a table, and this height is given as 0.74. You might have different numbers than I do. And we're going to put it on a bookcase up here. And the bookcase, they tell us, is 2.3 meters above the ground. So the book goes from here up to here. We know the mass of the book. And okay, how much work does gravity do on the way up? Really, we need to know what this distance is, because that's the distance that this actually goes through, this distance here. So 2.3 minus 0.74, 1.56. That's this distance from the table up to the bookshelf. So the work by gravity is going to be the force of gravity and then the distance that we go through. Now I could write cosine of 180, which is -1. But I know the cosine of 180 is -1, so I'm just going to put negative here. Again, the reason is it's moving this way. The force of gravity is that way. Here's actually the free body diagram. Weight, and then force by hand, something like that. Okay, and again, it's moving that way. Okay, so remember what the weight is, mg, and then times d. So we've got 1.4 kilograms, and then 1.56 meters. That's the weight, and then the distance we go through. Oops, sorry, I misspoke here. This should be 9.8, right? That's what g is. And then we got 1.56 meters. So m, and don't forget the minus sign, 1.4, g, 9.8, and then d, 1.56 meters. Hopefully you can read my writing okay. So we'll have to put all that together, and we have to put the minus sign in here. When you enter it in Mastering Physics, you have to include the minus sign as well. I got about 21.4. Anybody else get that? Excellent, thank you. So that's the work by gravity. Now, it's not too bad to get the work done by your hand because it's just the opposite of that. We're assuming we're lifting this up at a constant speed. The force by your hand would have to be bigger to get it going, but now that it's going, it's just going at a constant speed, and then at the end you just place it on the bookshelf. So this is the work by gravity. The work by your hand has just got to be the opposite of that. So plus 21.4 newtons. Work by hand, maybe. There. So now you see why I put the little part on the W here, just to not confuse. This is W weight, this is W work. Okay. Excellent. Any questions on that one? All right, good. Let's look at the next one. Let's see. A crate slides down a ramp that makes 20-degree angle with the ground. To keep the crate moving at a constant speed, Page pushes back on it with a 76 Newton horizontal force. Okay, how much work does Page do on the crate as it slides down the ramp? Okay, so we'll have to carefully draw a picture. This one's not as, this one's a little tricky just because of the drawing, but we'll put together a nice picture here. Okay, so here's the ramp. It is 20 degrees. Here's the crate sliding down the incline. So they're telling us that this, and you might have different numbers, this is 0.45 meters. So let's see. It's sliding down the incline. Now Page keeps it moving at a constant speed by applying a horizontal force. So Page's force is this way. That's what makes this problem a little tricky. We have to figure out how much of Page's force is actually this way, right, to get the work done by Page. So picture it, it's sliding down the incline. It would speed up, they're telling us, but Paige puts a force on it back this way. Actually, her force is this way. The part of it that keeps it going at a constant speed is that way, though. Okay? So if we could figure out Paige's force by Paige, I'll just call this x direction. If we could figure out this force, multiply it by 4.5, don't forget the minus sign because it's actually moving this way, we could figure out the work done by Paige. Okay, let me write this and then I'll ask you if you have any questions. Work by Paige minus force by Paige, x direction, and then I'll just put d, 4.5 meters, times d. We know the d part, we've got to figure out the force by Paige. And again, the minus sign comes from the fact that it's moving this way, Paige's force is back that way. Okay? Just to be complete here, we could put the weight on. That would be this way, normal force. Okay, we don't know anything about the friction. Maybe there is or is not. We don't need it for this one though. Remember how we did this before? If this was theta, this turned out to be theta. What we have to do is figure out what this angle is. We'll have to just be a little bit careful with it. So this is Paige's overall force. Good, so when we did two-dimensional motion, chapter 4, or chapter 3 I should say, this was theta, this was theta. This is 90 degrees here. This whole thing is 90. So this angle here is 90 minus theta, but this whole thing is also 90, so this turns out to be theta again. Okay, so carefully go through there, you'll see that that is theta. Theta, theta, 90 minus theta. This whole thing is 90, so that's back to being theta. Okay, good. So let's take a look at this and figure out which one of these is actually going to work for us. The formula has cosine of theta, but I don't know if this is the theta in the formula, right? So let's just take a look at it. Cosine of theta, looking at this picture, is the adjacent side. Okay, good. This actually is the adjacent side. Force by Paige in the x divided by the hypotenuse. Right, this is 90 degrees, so this is the hypotenuse. Force by Paige. So force by Paige cosine theta, that's what force by Paige in the x direction is. Okay, and that's what I need for the formula here. So without putting numbers in for this one, you've got to get how much of Paige's force is actually opposite the way it's moving. Put it back in here. Here's the displacement. And the minus sign again is because it's moving this way. Her force is the opposite way. Okay. Very good. Any questions on that one? All right, good. So kinetic energy, we've already been talking about it with the work energy theorem. So as you notice, it says K, 1/2 mv squared. I call it Ke because we're going to have spring potential energy, which also involves a K. So just to distinguish it, I'm calling it kinetic energy. So there's two different kinds of kinetic energy. Translational, that's the kind we've been talking around, just moving, left, right, up and down. That's kinetic energy. Now, if something is rotating on its own axis, that's rotational kinetic energy. And when we do circular motion, we'll come back to that. So we don't see it here quite yet. We have to do chapters 6, 7, 8, and then we'll talk about that. Okay, so the units turn out to be joules. You saw that in the lab actually as well. So it's the energy of motion. So something that has mass and is moving has kinetic energy. And here's an example. A two-man bobsled has a mass of 390. Starting from rest, the two racers push the first 50 meters with a net force of 270. Neglecting friction, what is the sled's speed at the end of 50 meters? Good, so we can use the work energy theorem to actually get this. You could have, knowing the force and the mass, you could figure out the acceleration. And then once you have the acceleration, displacement of 50, starting from rest, you could use kinematics to figure out how fast you're going. With the work energy theorem, though, we can just do this in one step. So let's solve this one and then look at another one from the homework, actually. And I'll write everything down here. Okay. So we know the mass, 390. Okay, starting from rest, initial velocity of 0, in other words. 2 racers push 50 meters. And then they jump in. We can neglect friction. Here's their force. And what's the sled speed after we've gone 50 meters? So we don't know that. Okay. So mass, velocity, force, and this displacement that we've gone through. So that's a kind of a hint to use the work energy theorem. And I'm assuming this force is lined up with the way that the thing is actually moving. I'm just going to represent this as a block. Normal force, weight, and I'm just assuming that this force is this way. Okay? So the work, FD, cosine of 0, which would just be 1, so I'm not going to write that. That's the change in kinetic energy, the final minus the initial, 1/2 mv final squared, minus 1/2 mv initial squared. So the work energy theorem that I gave you, I'm just picking out this part of it. This and this. Okay, initial speed is 0. Again, you might say, well, what's the formula for finding the final speed? There is no final speed formula. You have to use this concept of the work energy theorem. And then hopefully what you're looking for is in this formula. So we're going to have to do some algebra. This term is 0. So multiply both sides by 2. Okay, so again, that's 0. Multiply both sides by 2. Divide by the mass. That's equal to the final speed squared. So then we'll have to take the square root. Right? Multiply both sides by 2. All right, that goes away. Divide both sides by m. Okay, good. That would be v final squared. So then I take the square root. Okay? So it's we've saved a lot of time by not figuring out the acceleration and then trying to figure out which kinematics equation to use. We could just do it really in just a couple of steps here to figure out the final speed. Again, to save a little bit of time, I'm not going to put the numbers in there. Now just be careful with the units. Everything's in SI units. Force in newtons, displacement in meters, mass in kilograms. We're good to go with that. Whenever you put anything in an equation in SI units, it comes out automatically in SI units. All right, good. Any questions about that one? Let's look at number 15 from the homework. 15 from chapter 10. Okay, so Sam's job at the amusement park is to slow down and bring to stop boats in the log ride. Okay, so the log ride is the boats come in, the ride's over, Sam has to touch them and then slow them down. So Sam's force is this way while the log is moving that way. So Sam's work is actually negative. Right, the log's coming in, Sam grabs it, and Sam's force on the log is back this way. And that slows it down. Okay, let's see what we have here. If a boat and its rider have a mass of 900 kilograms and the boat drifts in at 1.8 meters per second, how much work does Sam do to stop it? So here we're actually looking for how much work Sam does. Is the work positive or negative? So it had, oh, yep. Negative, good. And why is that? That's correct. Good, reducing the velocity of the log, that's perfect. It's moving this way, Sam's force is the other way, so the work would be negative. Yeah, perfect, good. Slowing things down makes the work negative. All right, let's take a look at this one. Okay, so again, you might have different numbers than I do. Mass of the log and Sam, 900. Initial velocity of 1.8. And Sam stops it, so the final velocity is 0. So the work, you can think of the work energy theorem, there's a lot of parts to it. The part we could utilize here is 1/2 mv final squared minus 1/2 mv initial squared. So we looked at work in terms of force times displacement, but remember it's also equal to the change in kinetic energy, 1/2 mv final minus 1/2 mv initial. So the final speed is 0, so that actually goes away. Minus 1/2 mv initial squared. And there's the negative sign that we were expecting. So minus 1/2 900 kilograms, 1.8 meters per second. Don't forget to square it. So just to get an idea, that would be 450 times about 4 or so, less than 4, but 450 times 4. So you get an idea what it's going to be. It should be less than 1800. Let's see if that's correct. So 0.5 times 900 times 1.8 squared, 1458. So minus 1458. Good. So that's definitely less than 1800. Okay, good. Any questions about this one? All right, very nice. So here's one that we can vote on. Whoops, that you can't see yet. One day I'll get through the whole thing without saying, whoops, you can't see it. We'll see when that happens, though. A light plastic cart and a heavy steel cart are both pushed with the same force for a distance of 1 meter. So same force, same distance, and they both start from rest. After the force is removed, the kinetic energy of the light plastic cart is greater than, equal to, or less than the heavy cart. Or you can't tell because it depends on how big the force is. So same force over the same distance. Which one has the bigger, well, not which one, but is the kinetic energy of the light cart greater than, equal to, or less than the kinetic energy of the heavy cart? Or you can't say. All right, good. All right, excellent. Ooh, okay, good. Kind of a variety of answers. It's equal, the kinetic energy is equal. Now the light cart is moving faster, but its mass is also less. Those effects balance out. Remember, force times distance gives you the change in kinetic energy. They both started with no kinetic energy, so they have to have the same final kinetic energy. The lighter one will be going faster, but it has less mass. The heavier one will be going slower, but it has more mass. Kinetic energy turns out to be the same, though. Same work, same change in kinetic energy. All right, good. If you remember, we did this with momentum before as well. Any questions on that one? Okay. So potential energy, there's a couple of kinds we'll talk about. There's a gravitational potential energy and elastic potential energy. So this is the potential energy stored in springs, rubber bands, that sort of thing. Okay, forces such as friction that cannot store useful energy are called non-conservative. So once you introduce friction into the system, you don't get that energy back very easily. Okay, the lab that we do is really similar to this FET that I'm about to show you. So potential energy is really the energy of position. Okay, so here's a skater. I'm just going to set the reference point down here at the ground. We could grab the skater and move the skater around, actually. So if you notice, we're actually on Earth here, gravity 9.81. We can look at a couple different graphs. Let me pause the guy up here. So right here, we can say that the skater has potential energy, and the skater has really slowed down. I think I can do this frame by frame, actually. Okay. So this is the highest point. The skater's not moving anymore. It just might have started moving a little bit. So we got a whole bunch of potential energy. So what happens to the potential energy? Well, as we play this, actually, let me put a little graph here. So kinetic energy is going to be in the green. Potential is in the blue. We don't have any thermal energy because there's no friction. And this is the total energy. So let me just go slowly through here. So if you notice, we're getting less and less potential energy. Potential energy is the blue. And we're getting more and more kinetic energy. The total energy, though, is staying the same. The total is made up of kinetic plus gravitational potential. And then I'm just going to let it play. And then back. So as we go towards the bottom, a lot of kinetic, no kinetic. A lot of potential, no potential. And it just goes back and forth between both of those. And if there's no friction, this will just keep happening. On Earth, there's always going to be friction, though. I mean, you can try to minimize it somehow, but it's really hard to totally get rid of any friction. So when you see thermal energy in this class, for the time being, it's going to be attributed to the work done by friction. So things heat up if there's friction. The track actually would heat up. Probably the ball bearings and the wheels heat up. The wheels themselves heat up. So let me just add a little bit of friction, and you can see what happens to the thermal energy. Whoops. There we go. So right now there's none. I'm just going to add a little bit. So the red is thermal energy. This is more realistic, right, on the Earth. So if you did this, you're eventually going to start slowing down. What happened to all my total energy? Well, it's going into friction. You can have some systems where this goes on for quite a while, but here, eventually this is actually going to stop. Okay. Let me actually reset this. And then we'll get rid of friction again. So this is on the Earth. See the reset button. So the guy's still moving a little bit. All right. There you go. Let's change this to somewhere else. Maybe the moon. So the moon, the gravitational force of the moon is not as great as the Earth. So as numbers go, I mean, the guy's not going to be going as fast, right? There's not as much potential energy on the moon as there would be on the Earth. I can quickly change it to Jupiter, actually, where there's a whole bunch. I don't know if you can tell, but really down here we're going a lot faster because there's more gravitational potential energy because we're higher. All right, you ready for space? Right, there is none there. The guy had kinetic energy, and there's no gravitational potential energy because we're away from everything. So I launched the skater into space. Okay. So the lab, when it's available tomorrow, you'll be doing something similar to this. You can actually build your own track if you want to as well, and you can do that too. You'll see more about it when I give you the actual lab. But you could build your own track, put the skater on your own track. that sort of thing. Okay, so that's what, you've got something to look forward to, that lab available tomorrow. Okay, any questions about this? So we have the formula for kinetic energy. We don't have it for potential energy yet, but we will. Goodbye, skater. I watched this earlier today, and then I went and got a cup of coffee, and I didn't turn them off when I came back. I felt sad, like the guy was doing it the whole time when I wasn't even there. I apologize to him, though. So gravitational potential energy is the energy of position. So you can store energy here. So if you start off this book here, lift it up here, you've done some work on the book and you've stored some gravitational potential energy. Now if you move your hand and let it go, the book will head towards the Earth and turn gravitational potential energy into kinetic energy. You can have any reference point you want to. Usually we set the reference point to 0 here. It's really the change in potential energy that you want. So if this is 0, this is 5, this is 15, the change here would be 15 minus 5, or 10. So if you said that this was 0, this height then would be 15. It's really the difference in height that you're worried about, not the absolute 0 point. Okay? So here's the formula. Gravitational potential energy, the mass times g times y. So if you've had another physics class in the past, they might have just called this PE for potential energy. Here we call it U sub g for gravitational potential energy. And then again, usually you set this at 0. It's a so-called conservative path. It doesn't matter which way you go. If you walk this way, or if you head this way, when you get up here, you have the same amount of gravitational potential energy. So it's independent of the path you take. If you go over to the tech building and go up the front steps, or if you take the winding path, when you get to the doorway, you have the same amount of gravitational potential energy. The path doesn't matter. Okay? Running up the steps might take something called more power because you have a change in potential energy over a shorter amount of time, but it's the same amount of potential energy at the end. Okay? So in terms of the units, this would be kilogram for mass, and then meters per second squared. So this is a Newton, this part of it. Whoops. And then times a meter, and then a Newton meter is a joule. So all energy has the same units in this class. It's joules. Okay, good. Here's a quick check thing we can vote on. Starting from rest, a marble rolls down a steeper hill, then down a less steep hill. For which is it going faster at the bottom? So it starts here, goes down a steep, starts here, goes down a not as steep. If you're trying to think about it just logically, you think, well, this one's going to get here sooner, so maybe it's going to be going faster, or this one's got a lot more time to speed up. How do those effects play together? So we want to know which one's faster. Faster at the steeper, less steep, same, or you can't say without knowing the mass. Okay, good, excellent. Good, good. So like a variety of choices. So these started from the same height. Same height, same height. That means they had the same amount of potential energy to begin with. So at the bottom, what has happened is we've taken potential energy and turned it into kinetic energy. So if they both started with the same potential energy, they're going to have the same kinetic energy at the bottom because we've turned, again, potential into kinetic. So they're going to have the same speed then. Okay? Very good. So here's another one. A small child slides down 4 different frictionless slides. Rank in order from largest to smallest, her speed at the bottom. I guess if I was picturing myself doing this one might be the most fun, it seems like, because you really get steep here at the bottom. This is still kind of fun, I think. This one's maybe the one that's not as fun. Just a regular old slide, and it's not too steep, and there's a steep one. So which one, A through D? Ranking the speeds. While I was talking, you probably already voted, so let me see again real quick what you got. Okay, good. All right, good. Good, so same height for all of them, just like the last example with the marble, so same speed at the bottom. You know, one might get there quicker than the other, but by the time they all get there, they're going to have the same speed. So make a note of this on the second test. Usually there's something really similar to this one. Okay, any questions about that one? Okay, so that's gravitational potential energy, mgy. We also have elastic potential energy. The S usually means spring potential, but elastic potential, same thing. So if you have a spring in equilibrium, that just means like an uncompressed spring or a bungee cord that's not stretched. You can store energy. So if you push it this way, you store some energy. You can either stretch it or compress it. The more and more you press a spring, the bigger and bigger the force becomes. So in the beginning, it's maybe not too bad, but the more and more you push it, the bigger and bigger the force has to become. And you can store more energy there. Well, let me say something about Hooke's law. It says here, Hooke's law describes this. You won't see Hooke's law until you get into like chapter 8 of the book, so let me tell you what it is really quick. Okay, so if you have a spring and you compress it, some distance, Hooke's law tells you how much the force is. So if you read the chapter, it says minus kx. It gives you the direction of the force by the spring. So if I take the spring, and here it's relaxed, and I compress it by some distance x here, the spring force is back this way. Here's the force by the spring. This way. So the minus sign just tells you the direction of the force. I've put a force on it this way. The spring force is back that way. K is the spring constant. And the units are newtons per meter. And then X is how much you stretched it or compressed it. So you can see why I use KE for kinetic energy, because now we're going to have spring potential energy in a minute, which also involves a K, so it can be confusing. Okay, so this is Hooke's law. So we're assuming that it's the spring goes back to its normal shape. You haven't broken the spring or anything like that. And it's it works for springs in most cases, as long as they're not destroyed. Okay, so keep that in mind. We'll come back to it in more detail later on. Okay, so having said that, this is the formula for the spring potential energy. 1/2 kx squared. And again, k is the spring constant, it's not the kinetic energy. It's actually lowercase k, but it's easy to confuse it, especially if you're writing it on your own piece of paper. If you typed it out, you might see the difference, but if you're just writing it, it's easy to confuse those. So I would get in the habit of writing kinetic energy as ke. The units are the same again, joules. So it's the amount of energy stored in a spring. So we've got kinetic energy so far, gravitational potential energy, and spring potential energy. Now if you do see thermal energy, it's the work done by friction. Okay. Any questions on that before we take a look at the next one? Okay. So 3 balls are thrown from a cliff with the same speed, but at different angles. So these all have the same speed. They're coming from the same height. Which ball has the greatest speed just before it hits the ground? Okay, so this is ball A, thrown at some kind of angle. Here's B, thrown horizontally. Here's C thrown up at some kind of angle. So when they hit the ground, which one do you think has the biggest speed? Okay, good. Good. All right. Excellent. One more. Great. So the same height, so they have the same gravitational potential energy to begin with. They have the same speed, so they have the same kinetic energy to begin with. Kinetic energy doesn't really have a direction. So same gravitational potential, same kinetic initial, so they're going to have the same speed at the bottom. So each of them has the same total energy to begin with, right? For the reason I just said, same gravitational potential, same kinetic to begin with. So all of that, so that energy is transformed into kinetic energy at the bottom, the gravitational part of it. Okay? It's tempting to just try to reason it out like, all right, you threw this one down this way, so it's not going to slow down at all, it's just going to keep speeding up. But if you think about it in terms of C, all right, you did throw it this way, but now it's going to get to a greater height, right? And then all of that energy is going to be turned into kinetic energy. The idea that we're kind of using here without having talked about it yet is conservation of mechanical energy, transforming energy from one form into another. Okay, good. So here's an example we can take a look at. An archer pulls back the string of her bow to a distance of 70 centimeters, okay? That's perfectly good, but we'll have to put that into meters, right? We need it to be in SI units. From its equilibrium position. So if it's a bungee cord, a bowstring, those are all things that can store energy, elastic potential energy. To hold this string at this position takes 140 newtons of force. So the harder and harder you have to pull back a string of a bow, the more and more your force has to be. If you think about it, when you first start loading up the arrow, it's not that bad. That by the time you get to the end, it gets harder and harder. And then how much elastic potential energy is stored. Okay, so we know how far it was stretched. That's the 70 centimeters. It takes 140 newtons to hold it at 70 centimeters. How much energy have you stored? Well, the spring potential energy is 1/2 kx squared. We have the x part, that's the 0.7 meters. We don't have the spring constant part. Luckily, we can get the spring constant part from Hooke's law, this part here. Okay? So this is what's happening here. So Hooke's law, F is equal to kx. The negative sign just means the direction of it. So you can solve for k from Hooke's law, because F was kx, so solve for k. It takes 140 newtons to stretch it by 0.7. So the spring constant, the effective spring constant, not literally it's a spring, but it's a string being stretched, is 200 newtons per meter. And then you can take that and put it into this formula, 1/2 kx squared, to get the spring potential energy. Okay, so about 49 joules. And then when you release it, now you're going to turn spring potential energy into kinetic energy. Okay? Good. So 49 joules seems reasonable because the mass is not so great. Maybe it's moving pretty fast, but the mass of an arrow is not really too large. Okay? Any questions about that one? So again, whenever you see thermal energy, it's the work done by friction. So you could actually create some if you want to. Think about it like this. You move your hands together. You can really feel your hands heat up. Take a piece of paper, rub it on a table for maybe 20 or 30 seconds and touch it. You can feel that it's warm. So you've jostled all the molecules around. That's what's going on here. You can see them kind of moving around. So in this chapter again, thermal energy is the magnitude of the work done by friction. So if you happen to lose any energy for some reason, you could say that it's gone into to friction. Okay, so here's a box being moved across some surface. So friction on a moving object does work. The work creates thermal energy. And you probably couldn't feel this and feel something moving across the table, but if you took a picture like this that looks for energy, you could probably take a picture and actually see it that way. So if you take the kinetic frictional force, just multiply it by the distance that you go through, that's what thermal energy is. Okay, so we'll come back to that when we do the thermal energy chapters, chapter 12. But in this sense, it's just the work done by friction. Okay, let me see one thing here. Yep. So, vigorously rub your somewhat soft objects such as a blackboard eraser on a desktop for 10 seconds. This ought to work. I guess this is one of these. If you pass your fingers over the spot where you rubbed, you'll feel a distinct warm area. Yep, it's definitely warm. Congratulations. You've just set some, let's see, 3, 6, 9, 12, 15, 18, 21. So let's see, billion something atoms in motion. Okay, and you can actually feel the consequence of that. You can't see the individual atoms moving, but that's how many atoms are actually in motion, but you can feel the heat, right? The molecules are moving, hit the air, you feel the air that's warm. Okay, so we'll have to finish up chapter 10. So next week, I didn't say this yet, I don't think. Next week we will not meet on Monday. I'll make a video for the rest of the chapter. And then we will meet a week from today, which is next Wednesday. And we'll finish up chapter 10, any questions that you have. So what I wanted to do with the rest of the time is if you have any homework 5 questions. So if you took this class in West Lafayette, typically the way it works is you'd go and talk, you'd see the professor talk for like 50 minutes, and then you'd have recitation where you would just go work on homework questions and stuff like that. So the rest of the time, I'm just going to devote to like a recitation part. If you didn't have any questions and they didn't have a quiz, you might not even go to recitation, right, if you feel comfortable with it. So the rest of the time, you should. I'm not saying don't go, but you should. So the rest of the time, if you don't have any questions, you're caught up, you use the fall break to do that, you're free to go. If you do have questions, stay and we'll go over any questions that you have. So think of the rest of the time as recitation. Okay? And if you leave, I won't be insulted. That's just the way it goes. Okay? So any homework 5 questions? That's right, yep.
I was stuck on question 2.
The second one? Okay.
Yeah, I felt like it was simple, but I couldn't figure it out.
Yeah, let's take a look at it. A lot of times it's just the physics part's good, it's just the math part. There's something weird happens. Let's see. All right, see you later. Okay. Is it this one?
Impulse is Newton's times time, right?
That's good, yep. Now be careful with this because it's not a constant force. So let me just read it for everybody. Here's the picture. This is force versus time. In the figure, what value F max gives an impulse of 6 newtons times seconds? So when you have a force versus time graph, the impulse is the area under the curve. So you're right, impulse is force times time if it's the average force. But this is just the maximum force, so that's not the average amount. That's the trick with this one. Let's actually take a look at it. Do you have the same number, 6 Newton seconds? Oh, okay. Good, yeah, let's look at the area under the curve here. So again, impulse, change in momentum, average force times time. Or you could think of it as the area under the curve. So in this problem, they tell you how much the impulse is. 6 Newton seconds. So that's the area under the curve.